Okay, first of all, I would like to thank the organizers for giving me the opportunity to speak here. So today I'm going to talk about correlation functions in n equals 4 super mu theory and its relation to triangulation of the Riemann surface. And the work is based on, okay, so the talk is based on this work, and also there is related works written here. So the goal of my talk is to compute the correlation function of n equals 4 super mu theory from triangulation of the Riemann surface. So what is n equals 4 super mu theory? So n equals 4 super mu theory is a four-dimensional supersymmetric gauge theory. And in particular, I'm going to focus on correlation functions that are not protected by the supersymmetry, which is also called non-BPS correlation functions. And as you all know, the Riemann surface is two-dimensional quantity. So the first thing you need to ask is why there is such a relation, like which relates 4D and 2D. So the answer, the physics answer here is given by the ADS-CFT correspondence, or ADS-CFT duality. So the ADS-CFT duality relates n equals 4 super mu theory, which is four-dimensional conformal field theory with matrix degrees of freedom, to the string theory in ADS 5 times S5, which is 10-dimensional string theory. So n equals 4 super mu theory, you can do the perturbation, and each term in the perturbation is given by some, well, usual Feynman diagrams or ribbon graphs like this. And on the other hand, the string theory is, as you know, they're expanded in terms of the genus of the Riemann surface. So this duality is conjectured through the study of deep brains, but I should emphasize that the precise mechanism of the duality is not yet understood, even to physicists. So although the mechanism is not understood very much, we do know how the observables are computed on both sides. For example, let's take the correlation function of n operators in n equals 4 super mu theory. And we know that this kind of correlation function can be expanded in this form. This is basically the usual genus expansion. And well, of course, this right-hand side should depend on what you have on the left-hand side, so it has the index n, but well, this is a bit complicated, so I suppress the index in the rest of my talk. So this correlation function in n equals 4 super mu theory, this expansion is interpreted in this way. So this GS is inversely proportional to the rank of the gauge group, which is 1 over k. So this is why, okay, I should call it large K expansion in this case, but okay. So this is how the expansion is organized. And this GM basically comes from all the diagrams that can be drawn on a genus M curve. For example, this is the diagram that contribute to G0. So what I need to emphasize here is that even for G0, you need to resum all the diagrams. So there are actually infinitely many diagrams. And lambda here is the coupling constant of n equals 4 super mu theory. On the other hand, on the string theory side, GS basically controls the genus expansion of the string perturbation. And as you know, the GM lambda basically comes from genus M worldsheet. So on this side, there is like a no topologically distinct worldsheet. Well, you just need to, for example, if you consider G1, you just need to consider this kind of string worldsheet. Of course, there is a modular integral, but it's not that you need to resum very, very different things. And on this side, lambda basically corresponds to the size of the ADS. So although we know, in principle, how to compute the quantity on both sides, there is unfortunately difficulty, which is more or less the technical difficulty. So today I will basically talk about the genus 0 case, the planar case. But even in that case, it's actually hard to verify the duality. And the reason is because in n equals 4 super mu theory side, as I explained in the last slide, in the previous slide, you need to resum infinitely many diagrams in order to compute single G0 or GM. On the other hand, on the string theory side, you don't need to resum many diagrams, but it's just hard to quantize the sigma model in whose target space is ADS 5 times S5. So the method which allows you to overcome this difficulty is actually integrability. So let's see how it works in the case of like a two-point function, G0, 2. On the string theory side, it is known that the string sigma model is classically integrable. And using this fact, you can actually do the computation as follows. So one important observation is that if you consider two-point function, As I said, this basically corresponds to sphere with two punctures on the string theory side, which you can map it to the kind of cylinder, and the basically puncture lives at past infinity and future infinity. And actually, there is a kind of large amounts of literature on integrable models on a cylinder. So this is a cylinder, and you can actually use the methods to solve this theory. So it's called thermodynamic beta ansatz. On the other hand, in n equals 4 supermu theory, there is some relation between the operator which appear here and the spin chains. So the relation is like this. So if you consider a special class of operator called single trace operator, which is basically given by a product of fundamental phis and taking the trace, you can actually identify this kind of operator with a spin chain. Here, this is a kind of simplest case of identification. So you basically have two fields, z and y, and you identify z as up spin and y as down spin. And if you do this mapping, then you actually find that in n equals 4 supermu case, this spin chain turned out to be integrable. And you can actually compute this two-point function by computing the energy of the spin chain Hamiltonian. Then, and people further proceeded, and actually people found this structure, mathematical structure, which basically interpret this side and this side, which is called quantum spectral curve. So quantum spectral curve is a kind of general terminology, but here they mean very specific method to compute this kind of two-point function. So basically, two-point function is known. So what about the three-point function? So in the case of three-point function, on the string theory side, you need to consider sphere with three punctures, or equivalently, you can draw it as a pair of bands. And the emergence of pair of bands you can actually see also in the n equals 4 supermu theory side. For example, if you take the n equals 4 supermu theory and consider like a zero coupling n equals 4 supermu theory, so you set lambda to 0, then what you need to do to compute this three-point function is to basically do the wick contraction. And typical wick contraction you get in n equals 4 supermu theory is this kind of diagram. And for the important feature of this diagram is that the number of lines between the operator are completely fixed by the length of the operators. So this, as you can see, you can draw it on the pair of bands, and this pair of bands is characterized by the three numbers, L12, L23, and 31. But of course, this is simple because you are considering like a lambda equals 0 limit. But if you want to consider lambda non-zero, then you again need to face the difficulty of summing infinitely many diagrams. So the question is, can we use integrability to overcome this difficulty? And the answer, well, OK. To use the integrability, what you need to do is to basically to consider integrable models on a pair of bands. But unfortunately, people never studied this kind of like integral models on a pair of bands. So there is actually no literature that we can look at. But 2 years ago, we kind of proposed a framework which allows you to use integrability in this problem. So the basic idea is to cut the pair of bands into two hexagons. So this is OK. So I use the pair of bands notation, but you can, if you use this like a sphere with three puncture notation, then basically this corresponds to triangulation of the worldsheet. And OK, of course, I need to be precise what I mean by this picture. So in physically, what I mean by cutting the pair of bands into two hexagon is to consider the pair of bands and insert a resolution of identity of the Hilbert space on those dashed edges. So if you do so, then the three-point function is given by a sum of like infinitely many states which appear here. So what's nice about this here? Well, what's nice about this theory is because this theory is integrable, you can actually label the states by the number and the momentum of the excitation. So this is the leading term, which comes from the vacuum state, and which is a subleading term, which comes from one particle states on this edge. And these one particle states come with some measure factor and also some propagation factor. So remember, this L31 is one of the parameters which characterizes this pair of bands. And as you can see, this is a bit, in philosophy, a bit similar to Soen construction of 2D CFT, but what's different here is that usually in Soen construction, you just cut it into pair of bands, but here you further cut it into hexagons. And after doing so, the computation of the three-point function boils down to the computation of hexagons. And the question boils down to how to compute the hexagons. And here you can actually use the integrability. So I don't explain the detail, but the punchline is that you can use the symmetry, which is PSU's 2+2, which is actually basically almost the same symmetry which appeared in the last talk, and integrability to determine the contribution from each hexagon. So for example, one of the constraints coming from integrability is so-called Watson equation, which tells you that if you have a two-particle on hexagon, and if you swap the order of the particles, then you need to multiply S matrix, which is actually non-object. So by solving this kind of equations, you can actually determine the form factor, what's called hexagon form factor, or contribution from hexagon, well, which takes a bit complicated form. And well, here I just wrote the case for two particle, but you can also consider the case with multi-particles, and you actually observe that there is some factorization structure resembling Yang-Baxter. So this was the story for three-point function. Is there any questions so far? Okay. So then the next question is how to generalize this construction to like a correlation function involving more than three operators. Again, to gain intuition, we first consider the tree-level diagrams. And if you consider the tree-level diagram, to compute this four-point function in the zero coupling limit of n equals 4 super mu theory, what you need to do are as follows. So you first need to list up all possible planar graphs, and then compute the contribution from each graph. And typical diagram, tree-level planar diagram, is given in this way. And those diagrams are basically characterized by the number of lines between operators. So here you have like 6 different numbers, L14, L13, L12, and also L23, L34, and L24. And already here, you can actually see that there are actually 4 hexagons. For example, if you, in this typical graph, you have 1 yellow, red, green, and also a white region, and each of them correspond to hexagons. And in terms of puncture sphere, this basically corresponds to the triangulation of the Riemann surface for puncture sphere. So once you understand that four-point function is given by 4 hexagons, then you can do something very naive. Okay, so this is the diagram, the tree-level diagram you need to do. So you see 4 hexagons. And the idea is to do the same thing as for the three-point function. So the idea is to insert the complete basis on those dashed edges. And physically or mathematically, this means that this boils down to this kind of formula. So here, mu is the measure factor, which was already there for the three-point function. And this E2 minus EL is the propagation factor, which was also already there for the three-point function. And this L is just the number which characterizes the graph. And of course, there is hexagon. So what I'm doing here is to multiply this factor for each edge of this triangulation and multiply this hexagon amplitude for each faces of this triangulation. And then there is some factor which comes from the tree-level Wick contraction. So this is the naive proposal, but this cannot be true. And the reason is, in the case of four-point function, well, there is actually a very important difference between 2, 3, and 4-point function. In the case of 2 and 3-point function, basically the space-time dependence is completely determined, and what you need to compute is just this number or this number delta. But on the other hand, in the 4-point function, we know that it's a function of cross ratios. So you need to compute the function instead of the number. But the proposal I wrote in the last slide doesn't give you any like a rich structure of this function, of the function. So you need to understand how to incorporate this cross ratio dependence in this story. And okay, at the end, the way to fix was actually very simple. You just need to insert some additional factor here, which is actually cross ratio dependent. So then, what I need to explain is how to determine this cross ratio factor, because everything else is already known in the case of 3-point function. And what's nice about this is that actually this weight factor is kind of simply determined by the symmetry analysis. So to determine this extra factor, which is associated with the edge, let's consider the gluing of edge 1, 4 here. And you have 2 hexagons here. And by using the conformal transformation, you can bring the first operator to at the position 0, and third operator at position 1, and fourth operator at position infinity. And then the position of the second operator is parameterized by the cross ratio. So this is how the cross ratio works. And if you consider this situation, okay, so if you go to this configuration, then you see that the first hexagon is in a sense canonical because the vertices of the first hexagon is at position 0, 1, infinity. On the other hand, the vertices of the second hexagon is somehow rotated in a sense because they have vertices at position 0, ZZ bar, and infinity. And okay, so here I chose a very specific, like a conformal frame, but I can actually associate edge with cross ratio in more general cases. And actually, the relation is very reminiscent of the definition of the Fock coordinate in Teichmüller space. Okay, so this is the setup. So I said that H2 is rotated. So by this, because H2 is rotated, you can actually express H2 as a similarity transformation of H1, hexagon 1. And here, this G, and what is this G? And this G is basically the transformation which brings these 3 points into these 3 points. And it is actually very easy to figure out what this G is. And essentially, in order to bring these 3 points to these 3 points, you just first need to do the dilatation, and then you need to do the rotation. Then after doing this, the position 1 gets transformed into position ZZ bar. So, and written explicitly, G is given by this expression. And once you understood that H2 is related to H1 in this way, then in order to do the gluing, you basically need to consider consider the product of H2 and H1, and then use this relation to re-express H2 in terms of H1. Then after doing so, you discover that there is some additional, factor, which is the eigen, which is basically the, okay, something is not right, but okay. All right, so okay, I will continue explaining then while Jorg is trying to fix it. Okay. So this is the extra factor, which is basically the eigenvalue of this transformation G of this state psi. Yeah, I thought there is something wrong with the projector, but okay. Okay, all right, so, okay. Yeah, thanks very much. Anyway, I'm almost done, so. For the moment it works. Yeah, for the moment it works very nicely. Thank you very much. Okay, so this is the additional factor, and because you know explicitly what the G is, so you can actually compute this weight factor. And okay, so of course this was just proposal, and we need to do the checks. And the check you can do is to check the formalism against the perturbative computation of Feynman diagrams of n equals 4 super mu theory. And at one loop, the check is actually easy because you can, well, if you work out the details, you discover that only one particle states contribute to the final answer. Then if you write the one particle contribution, then you get this kind of expression. And essentially, this sine A phi over sine phi is related to the character. And the reason why you get the character is because here you have the eigenvalue of G, and you need to sum over all possible states. That's why you have the character. And okay, so this is a bit complicated object, but of course, what you need to do is to expand this at the leading order. Then it boils down to this kind of very simple integral. and sum. And if you do the computation, you get this nice combination of dialog and log, which is known to be coming from some Feynman diagram, which is called one-loop conformal integral. And I think this function is also called Bloch-Wigner function. And indeed, this reproduces the known answer. So this was the, one of the important supports of our conjecture. And actually, I'm almost done, but before finishing, I would like to mention one thing. Okay, so I have plenty of time. So our construction basically forces us to cut the string worldsheet into triangles. But of course, that it's often the case that the triangulation is not unique. For example, if you consider this kind of gluing, then you can also triangulate this this square in this way. And if you change this triangulation, then the cross ratio governing this gluing is actually z, whereas the cross ratio governing this is 1 over z. And although we don't have a proof, but we can show case by case that these two computations actually give the same result. And we are calling it flip invariance, well, because it's really similar to what happens in the case of triangulation of the Riemann surface. And indeed, this property actually is important because it guarantees the crossing symmetry of the full 4-point function. So now conclusion and prospects. So what I explained today is basically the integrability-based framework to study correlation functions in N=4 supermu theory. And although I didn't explain, but it works also for correlators involving non-BPS operators. And it hints the deep relation between triangulation of the Riemann surface and a correlation function of N=4 supermu theory. And as for prospects, of course, there are obvious next steps, like more points, higher genus. And also, as I said, this construction is a bit similar, a bit reminiscent of the Soen construction of the CFT, but the difference is that now we are cutting everything down to hexagons. So it might be interesting to try to get this 2D CFT correlator, such as minimal model correlator, from the triangulation of the Riemann surface. And also, it might suggest that there might be something like string field theory coming from triangulation. And basically, that's it. Thank you very much.